Okay, nice.
Yeah, good idea.
A few weeks ago, I was backstage helping out at the show of a young adult production of All Shook Up. We had just started the second act. I was getting ready to, settle into my chair, not have to worry about anything till the end of the show, when all of a sudden, everything starts shaking. Everyone starts running, and everyone starts freaking out. So, about a minute later, a solid minute later, of all this shaking, everything stops, and an announcement comes up that says, hey, everybody get out of the building, go outside onto the grass, and we'll have a head count. So naturally, we all did that. Today, I would like to enlighten you about the natural phenomena known as earthquakes. I've been researching this topic actually ever since those things happened. One thing that I like to do when I get really scared about something is to research it and figure out what it's all about. And that's what I did this time. I'm sure everyone here remembers the earthquakes and the about 100 aftershocks that we had. Those were a lot of fun. I'm sure you all agree. Today, I will help you understand these tremors of the ground by explaining how they are caused and how they are measured. First, how are earthquakes caused? According to Jerry Coffey, writer for Universe Today, there are two main types of earthquakes, natural and man-made. Man-made earthquakes are always related to explosions detonated by man, while naturally occurring, or tectonic earthquakes, occur along tectonic plate lines, or fault lines. These fault lines are where most, not all, but most natural earthquakes occur. And this is due to the fault shifting. Dr. Harry Joel, a professor of geology at University of Wisconsin, says this: there are three different types of fault: normal, reverse, and transcurrent, or strike-slip faults. This is a picture of the first type of fault shift, okay? As you can see, this wall block here is kind of on top of, if you can imagine that, this fault, where they're sort of like this. And they're shifting away from each other like that. And what happens is, when these faults shift, sometimes they kind of, gently pull on each other, and then one time, every few years it goes bam, and that's when you feel the earthquake. That is a normal fault. You go to the next one. Now this is a reverse fault, and as I'm sure you can intuitively tell, it's just going the other way. The one that's on top is now pushing into the one that's on the bottom. And they just kind of push into each other. It's the same sort of thing. Sometimes they push a little bit, and other times they push a lot of it. And that's when you get the different sized earthquakes. Now this is the weird one. This one is called a strike-slip fault, or a transcurrent fault. And basically, it's when the two faults, instead of being on top of each other, they're kind of side by side, and they just rub up against each other. These ones are typically the ones that actually give the littlest earthquakes, because when they shift, they don't shift on top of each other and cause everything to go crazy. They just kind of push on the sides of each other and cause little minor earthquakes. Now, knowing how the earthquakes occur has given us the possibility to measure the way the earthquakes affect the world around them. Earthquakes are measured using what is called a moment magnitude scale. Based on UPSIZE, a seismological education center, part of the Michigan Technological Institute, the moment magnitude scale is based on the total moment release of the earthquake. Moment is a product of the distance a fault moved and the force required to move it. It is derived from the modeling recordings of the earthquake at multiple stations. This basically just means that you've got the fault, and you've got a lot of little earthquake stations all around the place. When the earthquake hits, it hits all of these things at different times, allowing them to tell how far away the earthquake started. And because they're all in such, shall we say, precarious locations usually, it gives them a chance to see how much it affects the earthquakes, the surrounding area. These earthquakes then, the data on these earthquakes is then sent to the USGS, or the United States Geological Survey, where they interpret and record the data for the future. They're the ones who typically give out, it was an 8.0 or a 2.0 or a 3.5, something like that. The USGS has this to say about magnitudes. Magnitudes are made on a logarithmic scale, that's base 10. What this means is that for each whole number you go up on the magnitude scale, the amplitude of the ground motion recorded by a seismograph goes up by 10 times. So this basically means instead of when you go from 1 to 2, it's 2 times bigger. When you go from 1 to 2, it's 10 times bigger. And then it's 10 times bigger when you go to 3, which means a 3 is 100 times bigger than a 1. I'm sure you can kind of understand that. This, I know it's kind of blurry, but the words don't matter. This is kind of a graph of how frequently each of these things occur. This down here is a 1, and this up here is a 10. And as you can see, there are literally millions upon millions of tiny earthquakes every year. However, earthquakes like the one we had before, the 5.1, there are only about 20 in the entire world of those every year. And then up there where there's 9, there's barely one of those every, I don't know, 20 years. It's very, very infrequent that we get something that big. Just to give you an analogy of what it's like going from a 1 to a 2 or a 1 to a 3 or something like that, if you can imagine a 1 as being about 6 ounces of TNT, that's an explosion that could cause a big disturbance in this room and will definitely blow up a room that you normally sleep in. If that's a 1, an 8 is 6 million tons of TNT exploding. That would be like exploding this room, the room next door, and all of the rooms on campus. It's a much bigger thing when it's an earthquake. Because even a 1, even though you can't feel it, it still moves the ground. So an 8 moves the ground a hell of a lot more. Today, I have talked about earthquakes, both how they are caused and how they are measured. Hopefully all of you, like me, understanding just this little bit more will help you ease your fears of them in the future. Thank you.
I'm okay with it.
Okay, you suck. I was so sad.
Get used to it. Although not everybody does.
Good job.
Again?
I'm sorry about that.
So when we thought about
We
it,
did
I
tell you that was good.
don't know, it didn't bother me that much.
Brought to you by Toyo.
All right, Nick, I think you've got a good personal example for our attention device, and everybody can relate to it because it was a recent experience. The topic is pretty broad, but you explained where you're going with it, and I thought that the preview was very good. The explanations are fine. There were a couple of places where I think that you had this formula, for instance, at one point that you were talking about that probably could have used that visual to go along with it. I know you said that the images, the words on that last visual were not important, and I understand because I could see what the graph represented, but that doesn't mean that people aren't going to try and read it and that they're going to go, what does that say? What does that say? So that's a little bit tough. That would be one of those things, if you could clean up, that would be a nice thing to be able to do. The only delivery issues that I think are problematic at all are kind of unusual because most of what you're doing is really solid. Your voice is very effective, you have good variety, you project easily, so there's no problem there. Everything is fluent while you're speaking. If I'm watching your face, you're animated while you're talking to us. You step forward to emphasize particular points. All of your body movements seem like they are related to something that you're talking about. You've got lots of indicators, maybe a little more than necessary in the beginning. I say there's 2 of these and there's 3 of these, and maybe that might be a little bit more than is needed. But I could see that it was planned out and thought out, and so that was good. The one thing that is noticeable is the reading, because I know that you've got a lot of data that you have to read, and I think you'd be better off if you paraphrase the statistics in numbers and just talk to us, and only went to the notes for the direct quotes, and everything else you explained to us instead of trying to read it, because you read it well. And vocally you read it well, But watching you, there's just a lot of breaking between when you have to speak to the audience. Probably more than half of the time you're fine. All right, but that other half of the time, it's just very noticeable that you are dropping down and you're reading to us and that kind of thing. And the more you can get away from that, the better off you are. So that's the one thing that I think is a little bit problematic. All right,
Okay,
thank you.